Hi there! How do we represent the set of odd numbers using set builder notation? Set builder notation is really handy, so it's good to get some practice with it. I encourage you to take a minute yourself to think about how you would do this. There are many ways to represent the odd numbers using set builder notation. We'll go through a few of them in today's lesson. You may notice that what I have here is the set of odd numbers in roster notation. Roster notation is just listing off the elements that are in the set, and for an infinite set, we've got to list enough numbers so that the pattern is clear. You can see we've got -1, -3, -5, and so on, indicated by the ellipses, and so on in the negative direction, as well as 1, 3, and 5, and so on in the positive direction. So this has all the odd numbers. But it's often more precise and more convenient to use set builder notation. So how would we do that? Well, the most basic way, I would say, to represent the odd numbers in set builder notation is like this. Just say we want all numbers x, and then we separate this from the condition that we're going to specify using either a bar or a colon. So we'll say we want all numbers x such that x is odd. It's as simple as that. Using set builder notation, we say we want all numbers x on the left, separate this from the condition. On the right, we say that satisfy the condition that x is odd. So this is the set of all odd numbers. Now sometimes we might be a little more specific here on the left. Instead of just writing x, we could say that we're taking numbers from a certain set. So that z is the set of integers. So this would say we want all integers x where x is odd. However, every odd number is an integer, which is why it's not really necessary to specify that x is an integer, because the condition on the right that forces x to be odd forces it to be an integer too, because only integers are odd. All right, can you think of another way that we could represent the odd numbers using set builder notation? Well, an obvious weakness with this method of getting the odd numbers in set builder notation is that it's totally useless for anyone who doesn't already know what odd numbers are. If you gave this to someone to show them what the set of odd numbers is, it wouldn't help them. If they don't already know what odd numbers are, this is useless. So another way we might represent the odd numbers would be in some way that's a little bit more fundamental, that really gives us what odd numbers are. Now, what is an odd number? An odd number, you may recall, is any number of the form 2k plus 1, where k is an integer. So odd numbers are just numbers that are one more than multiples of 2. So another way we could do this is to say, again, here on the left, we're going to take all numbers x so that they fit this odd number definition. We want to take all numbers x so that there exists some integer k so that x equals 2k plus 1. That's what we're going to do. And instead of writing this bar to separate x from the condition, let me write the colon, these two dots, just to give you an example of that. I actually prefer this notation instead, personally, but you can use either one. If you're going to be using absolute value bars in your set builder notation, this is probably the one you're going to want to use. All right, so we're going to say all numbers x such that there exists an element of the integers called k, so there exists some integer so that x is one more than 2 times that integer. This is another way of specifying the set of all odd numbers that's actually useful for someone who doesn't already know what an odd number is. Up here, where we said x is odd, now we're saying the same thing, we're just actually writing out what it means to be odd. And by the way, if you haven't seen this symbol before, this sort of backwards E means there exists. So let's just check if some odd numbers that should be in this set are in this set based on how we've described it. What about the odd number 3? 3 should be in the set. By definition of how we've defined the set, 3 will be in the set if there exists an integer so that 3 is 1 more than 2 times that integer. In this case, that integer is 1. 3 is 1 more than 2 times 1. So you can see how that works. Another odd number, 7. 7 should be in this set, which would mean there exists an integer, so that 7 is 1 more than 2 times that integer. In this case, that integer is 3. 7 is equal to 1 more than 2 times 3. How about some negative odd numbers? Are we getting those as well? Well, how about negative 9? Negative 9 is a negative odd number. It should equal, if it's going to be in this set, it should equal 1 more than 2 times something. In this case, negative 5 would work. Negative 5 is an integer. That's our k value in this case. Negative 9 is 1 more than 2 times negative 5. 2 times negative 5 is negative 10, plus 1 is negative 9, so that works. But hopefully you're pretty familiar with the definition of an odd number, so you can see this definitely works. However, if we're going to actually use the definition of an odd number in our set builder notation, there's a much slicker way we could do it than this. Remember, here on the left, we don't always have to just put x. We can put useful information here on the left. We can say all numbers of some form such that a certain condition is satisfied on the right. Knowing that, here's a much nicer way that we could do this, and this is the way that I would do it probably. We're going to say we want to include all numbers of the form 2k plus 1. That makes sense, right? I mean, that's the whole idea. That's what an odd number is. It's 1 more than an integer multiple of 2. So we're going to say we want all numbers of the form 2k plus 1, and then what do we have left to specify here? What condition needs to be fulfilled? K needs to be an integer. That's it. K needs to be an integer. Odd numbers are defined to be 1 more than integer multiples of 2. If we didn't say that k had to be an integer, well then k could be anything, like, for example, how about 1/4? Then this would be 1/2 plus 1, which is 1.5. That's not an odd number, so that wouldn't do. K has to be an integer. So that's another way we could represent this set of odd numbers using set builder notation. Let's see another way. If you're familiar with modular congruence, here's another nice way we could represent the set of all odd numbers. We take all numbers x that are congruent to 1 mod 2. This modular congruence statement just means that when x is divided by 2, there is a remainder of 1 left over, which gets right back to that idea of an odd number. It's 1 more than a multiple of 2. So if you divide it by 2, you're going to get a remainder of 1. So this will give us all the odd numbers. The one change I might make to this set is to specify that x has to be an integer. As we said, odd numbers are integers, but the reason I would specify this is because modular congruence is defined for integers, not just for any real numbers. So as a human, if you were looking at this and we just said x instead of integers x, you would know that we're talking about integers because over here x appears in a modular congruence statement. But if you were doing this on a computer, if you were programming it, the computer very well would tell you, what are you doing? You're plugging a real number into a modular congruence statement. That's not defined. So I'd specify x is an integer. Now, one other thing we could do, there are many other things we can do, but one more I'll share with you. Odd numbers. Well, every integer, okay, is either odd or even. So another kind of silly way we could do this is to take every integer that isn't even. So we could say, let's take all integers, and here I'm going to say n, just to show you, of course, it doesn't have to be x, it can be whatever you want. We'll say we're going to take all integers n. Now if we eliminate all the even numbers, all we'll have left are odd numbers. So how could we specify that n is not even? Well, we could just write it Or another thing we could do is say that for every integer k, for every k in the integers, n is not equal to 2 times k, right? Because this is the definition of a number being even, is that it is equal to 2 times some integer. So if n is an integer, but it's not equal to 2k for any integer k, n can't be even, and so it will have to be odd. Take 6, for example. It's even, it's equal to 2 times 3. So it's not going to satisfy this because it is equal to 2 times some integer. And every even number is 2 times some integer. So this condition eliminates the evens, and we're just left with the odds. So those are a few ways that we could write the odd numbers in set builder notation. If you haven't thought about it already, I certainly encourage you to write some set builder notations for the even numbers, and see if you can come up with some other ways of representing the odd numbers using set builder notation. Let me know what you come up with, and if you have any questions, down in the comments.
The bride is in the hall, the silver out of sight, though the west wing haunts, Cupid twirls blind from the cracks of the bells, the arches spread light.